Hello participants, thank you for participating in Code Conquest. In this video, we are going to discuss the solution to the problem get the loot, which was the second problem of the contest. In this problem, it is mentioned that there is a loot and the loot is split into n piles and each pile has ai pieces of loot. So these are the n piles of loot and each pile has ai pieces of loot. So the 0th pile has a0 piece of loot, the first pile has a1 piece of loot, the second pile has a2 piece of loot, and the n-1th pile have n-1 piece of loot. We are using 0 based indexing over here, that's why I started with the 0. And n is the number of piles, so there are n piles over here. And it is mentioned that in each operation you can do the following steps. So in each operation you can take 2 pieces of loot from the ith pile and 1 piece of loot from the i-1th pile and 1 piece of loot from the i+1th pile. So you have to do these steps in each operation. So in each operation what you can do is that you can take 2 pieces of loot from the ith pile, 1 piece of loot from the i-1th pile and 1 piece of loot from the i+1th pile. And what you have to do is that you have to check whether you can make all the piles empty after performing this operation any number of times. So you have to check whether after performing this operation, inside a single operation you have 3 steps. The first step is taking 2 pieces of loot from the ith pile, taking 1 piece of loot from the i-1th pile and taking 1 piece of loot from the i+1th pile. And after performing this operation any number of times that you want, you have to check whether you can make all the loots, all the piles empty. If you can make it empty, you have to print yes, otherwise you have to print no. So this is basically an implementation problem. There is not much logic to think about. So you just have to apply this operation on the piles till you can no longer validly perform this operation. And after you perform this operation till you have to check whether all the piles have become empty or not. So that's what basically you have to do. But for implementation simplicity, what we can do is that we can start from the beginning, or you can also start from the end, but I am going to start from the beginning. From the beginning, what I am going to do is that in the beginning, suppose we are standing on the 0th pile. Suppose we are standing on the 0th pile. There is first pile after that and there is second pile after that. 0th pile, first pile, second pile. So when we are standing on the 0th pile, if the number of pieces of loot in the 0th pile, if a0 greater than 0, that means it has at least 1 piece of loot here. What we are going to do is that we are going to take that piece of loot from this 0th pile. Since this 0th pile has at least 1 piece of loot, we are going to take that piece of loot. But we know that if we take 1 piece of loot, we have to take 2 pieces of loot from the next pile and 1 piece of loot from the pile after that. So if you want to take 1 piece of loot from here, you have to check whether the first pile has at least 2 pieces of loot. We have to check whether A1 has at least 2 pieces of loot. A1 greater than or equal to 2 and the second pile has at least 1 piece of loot. A2 greater than or equal to 1. So if these conditions satisfy, you can take 1 piece of loot from here and you can take 2 pieces of loot from here and 1 piece of loot from here. But if the zeroth pile has some number of loops left. If A0 greater than 0, but either A1 less than 2 or A2 less than 1, then we can't take this one piece of loop from A0. Since the other two conditions doesn't satisfy, we can't take this one piece of loop from A0. So the operation fails over there because we can't make every pile empty. So the operation fails over there and we have to print directly no. But if we are able to successfully make A0 equal to 0 after performing these operations some finite number of times, we can move on to the next pile and repeat this operation. So after making this 0th pile 0, you will move on to the next pile, A1 to first pile, that is the first pile, and then after you are on the first pile, you will compare with the second pile and the third pile. So now you will repeat the same operation that we did on the 0th pile. We do the same operations on the first pile. And if you are able to successfully make A1 equal to 0, we move on to the next pile and we will repeat this operation till we can make all the piles 0. But if at any point this condition doesn't satisfy, we directly print no and we break out of the loop. But if you are able to make all the piles 0, we print yes at the end. So this is the brute force solution to these issues. So I will explain to you the optimal approach. The optimal approach is, instead of subtracting or taking one piece of loot at a time, what we will do is that we know that after these operations, what we want is that we need to make this ith pile or the 0th pile equal to 0, right? That's our final aim, and we have to do that for every ith pile of loot. But if we can't make the 0th pile equal to 0, we can directly break from there and we can directly print no. So how can we check whether we can make the 0th pile 0 without subtracting one by one, or without taking one piece of loot at a time? What we can do is that we will consider the entire A0 pile and we will check whether A0 into 2 is less than or equal to A1 and A0 is less than or equal to A2. If these are satisfied, which means that we can directly subtract A0 from A2 and A2 won't become negative. A2 will have sufficient pieces of loot if A2 greater than or equal to A0, and we can directly subtract A0 into 2 from A1 and A1 won't become negative because A1 greater than or equal to A0 into 2. So if both these conditions are satisfied, we can directly make A0 equal to 0 and we can subtract A0 into 2 from A1 and A2 into and A0 from A2. We can directly do this. There is no need to take one piece of loot at a time. But if either of these two conditions doesn't satisfy, we can directly break out of the loop and print no. So this is the optimized approach, and this will surely pass the constraints, and this is also the approach that we were looking for, and it is not getting accepted. So we will now discuss the implementation for the optimized approach. So the implementation is quite straightforward. So initially we have defined a vector called vec, and we are inputting the piles of loot inside this vector. This is equivalent to array or dynamic array in other languages. and we have initialized a variable called check initially and initialized it to true, and we are in, and if at the end of this for loop, if at the end of the iteration if check remains true, we will see out yes. Otherwise, if check has become equal to false at any point inside this for loop, we will see out no or print no. And now we will start the iteration from the 0th pile till the n minus 2th pile, while we are going only till the n minus 2th pile, because we are considering I plus 1 and I plus 2 over here. And if we don't, if we go till the nth pile, I plus 1 and I plus 2 will overflow or go out of bounds. So that's why we are only going till the n minus 2th pile. And I am checking whether the I plus 1th pile greater than the ith pile into 2, and the I plus 2th pile greater than or equal to the ith pile. So the I plus 1th pile greater than or equal to the ith pile into 2, and the number of pieces in the I plus 2th pile greater than or equal to the number of pieces in the ith pile. If these conditions are true, we can remove uh, vec of I into 2 pieces of load from I plus 1th pile, and we can remove vec of I pieces of load from the I plus 2th pile, and we can set the ith pile as 0 because we have used all the pieces of load in the ith pile. But if these conditions are not true, we can set check as false, and we will break out of the for loop, and we will print yes or no here. So this is basically the implementation.